Swayam Prabha. Digital India. Educated India.
So let us look into a little bit of corrosion issues and what people do there. So I will discuss mainly I will discuss wind turbine and this carbon capture and storage related corrosion issues. That's what I will majorly focus in this part, and little bit tell about these fuel cells and electrolyzers as well, and basically some other things from the literature rather, and then I just give a perspective for the other energy storage cases as well, and showing that what could be the corrosion issues. And when you look at, so all these are producing the, either wind turbine is producing the electrical energy, fuel cells and also produce electrical energy, electrolyzers on the other hand produce hydrogen as a fuel, and then this hydrogen fuel can be used in another place either to produce electricity or burn it and things like that. And so in all these cases, this power to X is also becoming important. People say power to X. Power to X means you are producing the power, and that power is used for running different things, for example. And so there is something in between here, and there it comes this important of these electrolyzers and things like that. So you produce a power, and the problem with the this renewable energy is that renewable energy is unpredictable, right? So you can, if it is oil and gas, you can produce oil and gas and store it and use it whenever you want. But renewable energy is concerned, it's unpredictable because you have to produce energy when there is sun, and you have to produce when there is wind. So that means that when there is excess wind or this one sun, and you need, either you have to waste the energy or you need to find a mechanisms to store it. So that's what people are trying with different ways of storing this energy, and that means that it can be used at a later stage for the application. So there it comes the importance of these electrolyzers, batteries. People are trying. I think somebody was mentioning also to me the other day that is so they work on supercapacitors, and supercapacitor is another way people are trying to store the energy like that. So there are many ways people are trying to store the energy, and then it can be used later. And there is corrosion problem related to this as well. So that, for example, electrolyzers means basically comes with that. There is a corrosion related to that. And there is, when you do the power producing and power then is converting into this, all this part, as a part of that, there are also a lot of electronics is used. So electronics also is an important thing. And we call it as a power electronics, because power electronics is a common name for the electronics that is used for the power conversion. So that means that you produce the DC voltage, you have to convert that to AC voltage because all the systems work in the AC voltage. And so then you supply as a AC voltage, but at the same time in the car, if you take the motor is running with DC voltage, so again AC has to be converted to DC. So AC voltage is the one that is easy to transfer from one place to another because the loss will be less. If all the power lines, if you are trying to pass a DC current, you will have a lot of losses. So AC current is better to pass through the line to another place. So that's why a DC has to be converted to AC. But then all these, many of the systems inside is running with DC. The DC has to be AC has to be converted to DC, and this is what they do. This power electronics do, and then so the efficiency of the power electronics, the corrosion of the power electronics also become important, which we will not look at it today. We will do that tomorrow. Take the wind turbine case, and wind turbine is one of the major things when you look at from the renewable energy system from the corrosion point of view. Basically because of the reason that wind turbine is a big structure, right? A typical wind turbine may cost in probably 250 million rupees to 500,000 rupees, and you can convert that into this one. And so it is a very costly system, and so that way the corrosion of that one is also has to be maintained. Like if you are using it for 25 years, it has to be maintained. It's also the reason that the wind turbine is the best place to put the wind turbine is in the offshore, and that also increases the chance for corrosion. That doesn't mean that there is no corrosion in the shore conditions. I'll show you later. There is also shore condition also have a corrosion, but much more in the offshore condition. And I mentioned this in the last days that typical example of a costly intervention, corrosion maintenance for offshore wind turbine, a typical maintenance which is cost about $50,000. So this is an also important thing. So that's also a reason that there is also another strategy which is coming up related to wind turbine, that is, I mentioned to you that earlier, proactive design and maintenance, which I will not take again today. I will come up with that together in the Friday's lecture. But let us look at the corrosion part of it. So if you look at the corrosion part of it, that is, this is the way you can divide the whole wind turbine system. You have the foundation, which is going into the mud below the sea. And there are many technologies related to this, like there is called this monopile, that is just one structure is going down like that, just a pillar sort of thing. And there are another thing that is with many lets. There are different technologies related to this, putting it under the sea. Now they are also thinking that floating type of thing. Floating means entire thing will be floating in the sea, but then there is something attached to that just to stabilize it, like that. So it is like a stagnant ship which is existing in the sea structure like that. So that's a foundation. Then there is this substructure part here, this one. So then this tower part which is coming, then there is a nacelle where all the part of the wind turbine is sitting, and then you have these rotor blades. Rotor blades itself is not a concern from the corrosion point of view that much, because why? No, that's not the case, because you will see a lot of corrosion in the nacelle. Yeah. No, it is made of, it's not made of metal. It's made of composite. So it's made of the polymer composite. So the corrosion issues, like the corrosion is what we are talking about, the metal thing is not a problem for these blades. That doesn't mean that there is no degradation for the blades, but there are other degradation mechanisms like erosion, because it is moving against the wind, right? So there's erosion, corrosion, there can be particles, and now it is rotating with a very high speed, so that even the small particles which is hitting on the surface can hit forcefully, and that way you can have other problems for the rotor blades, but not the corrosion, but we are talking about the metallic parts, because it's not made of metals. So these are the kind of things which we have in the wind turbine, but we can also see the corresponding, you have the different corrosion problem. Means the not corrosion problem, the exposure environment is also different. You have this inside the tower corrosion. Maybe the inside the tower you have environment is a little bit more benign, right? Because some way this one has to enter into this one, so it's not directly exposed. So that way the condition inside the tower is, this tower is open tower. So it's like a size of probably the base of the tower will be the size of this room. I don't know whether you are familiar with the wind turbine or not. So the wind turbine, that structure, if you take like this one, so it is like a kind of the width of the diameter of this comes down as we go up, like that. And the bottom part of this part, if you take, maybe the biggest wind turbine will have the size of this room. If you take the diameter here, and inside the tower, it is like a building. You have the lift, and through that lift you can go up. So you can take the lift from here and you can go up to the nacelle. Then there is an opening to the nacelle and you can get into the nacelle, and that's the way the technicians and all go up and then repair different things in the nacelle. So it's an open structure inside, and there is a lot of equipments that is sitting inside the tower as well, like a lift and other things. So the corrosion inside the tower is also important. So it's not, because there are so many things which is sitting there. So inside the tower, and this for example submerged zone. So if you look at here, so you have which is below the sea, you have the part, and you have this part that is a splash zone. So you have different corrosion here, because this seawater is splashing, and when the seawater is splashing you get much more corrosion here. Why? Alternate weighting is one thing, and also because of the higher amount of oxygen that is coming, and then you have a higher corrosion problem, that is splash zone corrosion issues. And then we have the atmospheric zone, which is mainly the nasal part, where the aerosols and things like that is coming up, and that way you have the corrosion problem in the nasal. So that's the way we can divide the corrosion problem in the wind turbine. There is, that's what I'm saying. So this part as well, like there is corrosion problem. Of course, it's not necessary that all these corrosion problems are relevant for everything, but there is corrosion problem. Like for example, here also you can have the differential aeration. Depending on the oxygen concentration, that kind of corrosion in that. You can have the microbes, which is sitting there, and microbial induced corrosion. And these microbes can also produce hydrogen as a metabolism mechanism, and that way you can have hydrogen embrittlement issues here. And if you look at, there is a lot of fatigue loading here, right? Because when this is rotating, although we don't see it, there is a lot of vibration for the tower. And because of the wind in the sea, this is actually a little bit flexing. So there is a lot of fatigue loading here. And that means that if the hydrogen is going in, then you can have hydrogen embrittlement, which is assisting the fatigue failure. So the mud zone also has a problem. But the only thing is that maybe from the corrosion point of view, more issues are here rather than here, because this is inside the mud, and that way the corrosion is less, but because of splash zone, there is much more corrosion in this area. So waterline corrosion, that is pitting due to the differential aeration in this area. Again, they say that it's pitting, but again, that depends upon which material you are looking at and things like that. And of course, this is probably, all these are heavily painted. So since it is a painted structure, the paint is delaminating, and that way you have the corrosion problem. So it's not, that's the reason that you will not see, very seldom you will see that really uniform corrosion. So it's a paint delamination and corrosion which is happening underneath. Stagnant water causing environmental discrepancies. Again, as I mentioned, that you shouldn't take this as a kind of a possibility everywhere. It depends on the conditions. For example, if the water layer is stagnant here, and then you can have that change in the environment here, chemistry of the environment, and that way you can have additional problems which different from probably in a seawater condition where the water is always agitated and things like that. And welding corrosion is many places. That is, welding corrosion can be there anywhere, because there is a lot of welding in this tower, and all the weld region is more prone to corrosion. Not outside that much, but if you take the inside the tower, the paint layer thickness will be less inside the tower compared to the outside. So that inside there is much more chance for the weld corrosion compared to that of outside. You will see that later, that they put a very, very thick coating outside to reduce the corrosion problem. Acidification, if sacrificial anodes are installed, that is, the sacrificial anodes are there, and that means that metal dissolution is taking place in the artificial anodes, and that is creating an hydrolysis, and that way it produces the acid conditions. That acid condition is in turn affecting the corrosion of this material. Yesterday we were talking about the other side, right? We were talking about the protection of the aluminium with the magnesium, and we were telling that if the magnesium is bringing the potential of the aluminum so much, then you can have more cathode reaction on the aluminium, and that way you produce the hydroxyl ions. That way you can get self-corrosion of aluminium because of the stability of the aluminium is not good in the alkaline condition. That's the other part. But now we are talking about the another problem with the cathodic protection, that is, if the anode is very close to the material here, and anode corrosion will create an acidic condition, because the material is dissolving and hydrolyzing and producing the H+ ions, and that is affecting this one. Then there is accumulation of gases. You will see that H2S, CH4 and things like that in the sea conditions, and also in the farm conditions and things like that. There is a lot of gases also can be in the atmosphere. So it's a very complicated systems, and you have the different corrosion problems if you take at different places. Certain corrosion problem here, certain corrosion problem here, certain corrosion problem here, and also with the change in the environment. If you look at the use of the wind turbine today, I think I took the European statistics. You can see that Denmark has around 70%. If you take the overall capacity, UK has 54%. That means UK has a much more wind turbine if you look at it overall compared to Denmark. But actually, if you take it, Denmark has much more wind turbine per area if you take compared to that of UK, because UK has a bigger area compared to Denmark. Otherwise, Denmark is in the top in the wind turbine installations and producing the wind turbine energy. But you can see that there is a lot of wind turbines, just to show that there is a lot of wind turbine installed in the places, and many of these wind turbines are in the offshore. Now we just look at a little bit on the material, and again this is an example of material used in the material used in the wind turbine. Is not necessary that all wind turbines have the similar, exactly similar thing. But what you see here is that there is a combination of steel, including stainless steel for some components, and a combination of aluminium. And there is copper. Copper is mainly related to electrical applications. You understand? Inside the nacelle, if you take, you have the this generator which is producing a lot of electricity, and this generator has to be connected to electronics. So the power has to be transferred. And what is the material usually they use it for power transfer? Either aluminium or copper. Why they use that? Higher electrical conductivity. So most of the cases inside the wind turbine they use the copper, and so that's why this copper you see that. So mainly it is related to electrical applications, and aluminium alloys are used not as a main part of the structure, but inside this nacelle there is you need to assume that the size of the nacelle is this room, so it's very big actually, and so there is a lot of cable trays and things like that. Cable is passing through that, and that for that purpose and all they use the aluminium structure inside, which is not loaded. So that's the reason that aluminium is used. So inside the tower there's a staircase which is made of aluminium, lift part is made of aluminium, and all those things. So it's not the load bearing structure is always steel in the case of wind turbine. So only accessory materials are made of aluminium, which also shows that corrosion of aluminium is not important. Even if the staircase corrodes a little bit, it doesn't matter. Even if the cable tray in the nacelle corrodes a little bit, it doesn't matter like that. But much more important is maybe corrosion of steel parts and like things like that. So there is a lot of steels and stainless steel and things like that. And now if you take the other side, the blade side, not the blade itself is, but it is the some of the other parts of the blade. If you take, again there is a combination of this aluminium and steel material. That's what you see. Taking away the electronics part, electronics I'm not discussing, but electronics part, these are the kind of things you see. Now it's understandable that the corrosion problem here, because you have the seawater to splash and create a lot of corrosion. You can see that this because of the agitation in the sea, this chloride condition will be existing all over this, right? Because there is a lot of aerosols will be coming inside the nacelle. Usually the air is filtered, so all the air which is getting in the nacelle is filtered. But as I wrote here, there can be still chloride conditions inside the nacelle, although it is filtered. And also this filter is only, whatever filter is there, it's only for aerosols, particles. That means that there can be H2S gas in the air, and the H2S also can get into the nacelle because the gas, it can diffuse into the nacelle like humidity. It can also diffuse into the nacelle if the turbine is placed a fan blade. I'll also show you some examples for that. And so it's not like a nacelle condition is perfect. Inside the nacelle you can have the chloride conditions and you have the H2S condition. Humidity part is concerned, it depends on the time. So when the wind turbine is working, this gearbox inside the wind turbine is producing a lot of heat, and that way the humidity is displaced. But most of the time the problem with the humidity comes when the wind turbine is not working, and that means that this wind turbine can be shut down for 2 to 3 months for repair work, and then the humidity inside the nacelle will be very high, and that's the time most of the corrosion is taking place. So if you take the structure, you can see like this, that is, you have the wind turbine with blades, Then that is connected by this shaft to the gearbox. And then gearbox is connected to, so the gearbox is to increase the number of revolutions coming from here. And then that is transferred to the generator. Generator will produce the electricity. That electricity is then converted into by using these electronics here to regulate, and then that is connected to the grid. So this is the way it works. So mainly the copper parts which I am talking about is the generator to these electric connections here, and many of these parts are made of copper, because what you are talking about is very, very high current. So you need to have a real copper bar to take that current. So it's not like a small wire is not enough to connect between these two. So real copper bar is needed to connect between these two. So that's more or less a structure. So that's why I tell you, if wind turbine is working, this gearbox will generate a lot of heat, and that way you have a lot of low humidity inside. So most of the time when the wind turbine is not working, and that's the time you have the problem. Electronics part, which I'll come tomorrow, but you can see that electronics is one of the most sensitive things in the wind turbine. So people have done a lot of studies related to wind turbine, and you can see that the failure data shows that in Germany, Denmark, and Sweden, they did a survey of the different wind turbine. So this, wind turbine is a big system, right? So they need to understand the corrosion related to each subsystems. That's the way it is. Like, what is the corrosion of the tower? What is the corrosion of the gearbox? What is the corrosion related to the this one? And they need to know that how much time it is taking for the failure, because all this information is important to do that things what I told, proactive design and maintenance, so that they can plan everything, and this is important. So they did a lot of studies looking into what is the, if you take the different sub-assemblies in the wind turbine, what is the kind of failure time? So they found that electronic sub-assemblies is a major cause of failure and downtime, 30% up to 30%, and this failure rate, and around 32% of the downtime is due to the electronics. What it shows that is electronics is the one causing many failures in the nacelle, and that way you need a frequent visit to the nacelle for repairing it. That is what is another way it is shown here. So they also calculate the mean time to failure for different sub-assemblies. It shows that an electronic failure occurs every 30,000 hours, compared to that of a mean time to failure for a gearbox, which is around 87,000 hours. That means that by the time a failure occurs in the gearbox, you need to have 3 visits for the electronics, because you could expect that within that time at least 2 to 3 failures of electronics, because the mean time to failure is almost 1/3 of that. Now we can also see that how this knowledge will help them to plan as well. So electronics is one of the weakest link in the wind turbine, and especially with the use of wind turbine in the offshore conditions, it is becoming much more worse into that. We will look at that in more detail tomorrow. The reason that nacelle is, as I told, the nacelle condition is quite good if the wind turbine is working, because the gearbox is producing a lot of heat. So the most of the problem comes when the gearbox is when the wind turbine is not working. When wind turbine is not working, this is very, very cold, right? Because you need to think that this is like a very thick metallic sample. The problem with the very metallic sample from the corrosion point of view is that metallic samples, it takes time to heat up, it takes to cool down. And this is where the atmospheric condition, the corrosion problems becomes more important. Like, I don't know whether that occurs here, but if you are, maybe this occurs here probably in the December, January time. Have you seen that in December, January time, when you go out, you look at the car, there is a lot of condensation on the car. Have you seen that? And the reason that condensation is happening, because in the night, the temperature was colder at that time, and there is more humidity in the air. And morning, the sun has risen, so atmospheric temperature has gone up. But the car will take a little bit of time to heat up. So since it takes time for the car to heat up, car is still cold and the condensation occurs in the car. It will be there only for about an hour, and after 1 hour it disappears. So this is exactly what happens in the nacelle. Like overnight, if nacelle is off, because of this delay, that's what is shown here. Kind of, this is with a PCBA which is shown, but there is a delay between the PCBA temperature and external temperature. What you can see, that is the PCBA temperature is rising, but this PCBA temperature is still colder like that. So this difference, and that is what is making the condensation inside. So the PCB as an example, but you can think about any material that is sitting inside, and that causes condensation at many different parts because it's heavy metallic parts, and then you get the corrosion problem. Like here, like if you take any level of humidity, and if you make the things cool, and then you can see that you get condensation. Like if you take a beer can from the refrigerator and keep it outside, you get condensation because beer can is cold and outside air is hotter than that, and then you get the condensation like what you see in the car. And these kind of things are accelerated by the chloride deposition. So if there is a chloride deposition inside, these things will be accelerated. We will look at that in the last lecture, that part, and how this deposition is assisting and things like that. So what we did is that in our work, that is, we did a lot of work with Vestas is one of the company which produce the wind turbines in Denmark. This is one of the world leading company producing the. There are very few companies producing wind turbines. There is Vestas, and which is a Danish company. There is Siemens, and the Siemens part is also in Denmark. Actually, the wind turbine part, there is an Indian company called Sustaintable or something like that, right? Yeah. So that's an Indian company, and there is a Spanish company. So not many. There's probably there are 7 or 8 companies producing the wind turbine, and Vestas is one of the leading company, and the almost half of the Vestas is in Chennai. I don't know where it is located, but half of the Vestas in Chennai. And we did a study with them because we did the kind of a corrosion analysis. So in this particular case, at that time when we are doing it, we use the corrosion coupons. So we take, I think there is silver in it, copper in it, zinc coupons, aluminum and steel. And all these coupons like this, which is a standard method, which along with the humidity and temperature sensor, we keep at different parts of this wind turbine, and we keep that there for 1 year. And after 1 year, we take it out, and within that 1 year period, this is collecting the humidity and temperature data, and this one is getting corroded. And after 1 year, we can analyze the corrosion level, and from that we can determine that what kind of environment was there inside the different parts of the wind turbine. One thing we get about the corrosion product, we know what it is, and from that we know that we can predict the environment, corrosion level, we can come with the corrosion class corresponds to the wind turbine, and all this information is useful for Vestas to plan different things. And we exposed such kind of coupons, not one place, that is bottom of the tower we had, top of the tower we had a place, this one, in the hub that is inside this here. This part we had sensor inside the nacelle, and nacelle you had the front of the nacelle and back of the nacelle, because back of the nacelle is the electronics is sitting in the back of the nacelle. So all these places we had coupons, and then we take it out and then we analyze. Finally, we see that corrosion class varies with the position inside the turbine, that is almost like C1 to C4. So if you get a C1 class of corrosion class in this part of the turbine, but there may be C4 here below. So that means that all over the turbine, we didn't expect that as well, right? We know that the corrosion class is different depending on the place of the turbine. And inside it can be much more cleaner compared to that of below, like that. So that way we see this C1 to C4, and we also, I'll show you a little bit more detail on that. And the corrosion class varies also with the installation's place, which is almost like C1 to C4 inside the wind turbine. So after some time, we take out the coupons, for example. So you can see that these coupons are corroded. And you can see that this is one of the seaside installations, which is, in this case, coupon is outside. Outside means it was in the hub here, or maybe it's a nasal roof or hub, and there it is directly exposed to the environment, and you can see that it's almost like the steel is completely corroded and broken. So these different levels of chloride, we can quantify that. So what we do is that we take these coupons and we remove this corrosion product by this cleaning method. So we do either, for example, copper and silver is concerned, we can also do the electrochemical reduction process. So put and reduce the copper oxide and silver oxide. So we can also do an electrochemical reduction process, but for the other metals we cannot do that, and we also do this cleaning process, and then we analyze how much it has corroded from that. And we do all these, I'm not showing everything, but we do SEM, scanning electron microscopy, and things like that to get a detailed idea about what is happening. So here you can see that, like for example, this is, I took one wind turbine to show you as an example how it changes. So this is a nasal roof. So top of the nasal, it is outside. This coupon is sitting outside on the nasal, and that collects the humidity data. You can see that this blue color must be the, blue color is the humidity data, and you can see that humidity is always 100% outside. So it's always saturated humidity level outside, and so that means that there can be a lot of corrosion problem there, and that's what you see here, because that table I will expand. So if you look at, you get a corrosion level almost quite high level here, and especially for the steel around about 38 micrometer per year, and that's what you get in the nasal roof. But the important thing is that I put this slide, I'll show you the next slide as well, another slide, to see that in the same wind turbine how it varies. That's the important thing. So this is outside, and if you look at here, so here you can see that now from the level of the corrosion we can determine the corrosion class. Corrosion class is C3. So if you take a C5 as a C side, and you can imagine from the C side, and CS is inside the C, and C3 is, C4 is somewhere away from that farmland. So around that condition, the C3 and C4, and that's the kind of level at which you have the corrosion right here. And then we go to the inside the nasal, whatever is put, and there we determine, and we see that the corrosion class is C1, and you can see here that is the corrosion rate is much lower compared to that of outside, inside the nasal. That you can also see from here. Inside the nasal, the humidity level is much lower most of the time. So here you can see that humidity level is probably only around 60% or 50% or something like that, except in some time it has increased, but otherwise humidity level is lower, and that also gives a less corrosion rate. And this is, so there you can compare, that is corrosion class 3 outside, and the corrosion class is coming to C1 inside the nasal on the same turbine, for example. Oh no, I think it is, that is, you need to ignore that. Basically what it shows, that is the corrosion was so low here that just ignore that value and take it as 0, because that is, the corrosion rate is so low in this case, and when we clean it and a little bit of material is removed from the cleaning process, and that is what you see that. So it's 0 basically. I think, I don't remember exact size, but it's a standard. It's an ASTM ISO standard, and I think it is, if I'm correct, it is around 4 or 5 centimeter, and this width is around close to 1 centimeter or 1.5 centimeter. Yes, this is one set. Like if you look at here, this is one set, like this way. So you have a plastic board, and it is put like this. If this is what you are asking. So each one is one material. No. If I understand correctly, this is the whole thing is kept at different places. So everywhere you have all these materials, and you have a humidity and temperature sensor. So we get the humidity and temperature data from everywhere over this 1 year period, and also we get the corrosion rate. That's from the each material is concerned, not everything, but for example, iron is concerned. People have done the experiment and classified into C1, C2. Similarly, zinc is concerned, there is a corrosion class and everything. So all these are based on. So if you look at here, the copper, iron, this distribution of iron, distribution of zinc here, like that, and based on all these is approximately the C3 class. So it's everything is considered here. So put in other way, in the C3 class, corrosion of iron will be higher compared to corrosion of zinc. Corrosion of zinc will be lower in the C3 class. C1 class also the ratio will remain almost. So it's based on all of them, it is coming to the C3 class. That's the idea. So it is just compared with atmospheric corrosion data where it is classified into the C1, C3 level. Approximately, I'm not saying that it is certainly matched with that, but that way it is classified as C3. Is that what you're asking? Yeah. So it's not just based on one metal, but it's considering the whole different things like a distribution of the copper, zinc and iron. It's yes, exactly. Similarly for the zinc as well. And so you can see that basically if you take this value of the iron and this value of the zinc, in both cases it is close to C3 like that. We analyze the corrosion product, then we do the SEM analysis and we analyze corrosion product. The important thing here is to show that there are many things you will see here. Important things to show that is it has chloride. So this is coming from inside the nacelle. This from inside, there's a spelling mistake there. It's inside nacelle, and you can see there is chloride and there is sodium, which also shows that this must be the sodium chloride. So although the air is filtered, still some aerosols are getting into the turbine, and that is probably causing this chloride to see there. You can also see a few other things. There is sulfur. So probably the reason is that there is some sulfur gases in the environment which is also entered into the nacelle and also created some sulfur containing compound. But we couldn't answer at the same time, that is why this phosphor is coming and like that. So because it's too complex actually. But on the other hand, ignoring that is some of the things which we don't expect, but if you take the other one, at least we can see that there is chloride and sulfur. And we also have seen that actually when we go to a farmland and where we measure the sulfur gases, we could see that there is sulfur gases in the air. And this is another analysis. Again, you can see that there is chloride, and there is a lot of chloride here. And so it is showing that it is like, although it is air is filtered, and still the chloride can be there inside the nacelle. And if there is chloride, again, you will see that the last class, that is, you don't need high humidity to get the condensation, right? Because chloride is hygroscopic, so that way you can get condensation with the lower humidity level as well. Why all these we have done? Because all these, yeah, this is another one. It is still showing that is same thing, that is there is chloride. So it's everything is to indicate there's chloride. Why we did all this? Because we did this in Denmark, China, Uruguay, Peru, Nicaragua, Dominican Republic, Chile, and Chile farmland, coast and farmland. So this is like little bit in the world at different places to identify that what is the corrosion class, more or less. So once they know the corrosion class, actually this Vestas, this company, can make a better decision related to how they want to supply and make the wind turbine. So one of the things which they found was that, for example, I think it was related to this, some of this, like this lower class, actually the places where there is a lower corrosion class, actually they sell the wind turbine which is made for C5. So they don't want to take the chances. So they sold the wind turbine which is made for actually for C5 class, and that was not needed actually. So they can save the material, and they can save the customer can save the cost and things like that. So you can see that understanding this, there is a lot of benefit by doing this. And but I'm showing here only a little bit of part of that. We are much more proceeding on this. Now But the problem with this measurement is that we use the coupons, right? So coupons, we keep it for 1 year, and 1 year it is blind, right? We don't know what is happening. But now we made a sensor, and this sensor is online sensor, and so that we can get the real-time data like humidity, temperature, and there are two other sensors which is determining the condensation possibility and things like that, so that we can get much more online data by using that one. So that makes it much more easy. We don't have to wait for 1 year like that. That's one thing. Second thing is that like we made a, see here we have the corrosion class we measured, right? And in all these places, basically all this corrosion is coming because the external climatic conditions, right? The humidity and temperature. So we made a climate app which this company can use. The climate app, looking at the climate app, they can understand that if they want to know that what is the kind of climatic condition here, and they can easily find that. And not only that, once they find the climatic condition, that one, you can look at what is the corrosion class there, that also they can find. That corrosion class in that climate app is not coming from our testing, that is coming from, you know that SICRI is having atmospheric corrosion test place, right? SICRI is having atmospheric corrosion test place at different places. Probably you have, right? Your institute having, your building research institute. Do you have atmospheric corrosion test site? No, you don't have. Okay. But SICRI is having, I know that SICRI is having atmospheric corrosion test site at different places. Similarly, in the world, there are many places there is atmospheric corrosion test site, and all these people have made the corrosion class related to it. So what we did is that I'll show you that in the last class that we made the climate app. That means that all the climate data from the world we collected, and we use the machine learning algorithm, and using the machine learning algorithm, we group this climate to say that entire world can be divided into few zones of high climate, low climate, and things like that. Not only that, then we overlap this climate, this atmospheric corrosion data, which is collected from different atmospheric corrosion site into that, and so that you can also know that this region is having C4, C5, and all those things. So now we overlapped their corrosion data, but now this, what we are trying to do is that since we have data at different places, we can interpolate. And that way we can make a little bit more information on that. But I'll show you that. So this climate app is helping the companies to take these decisions so that they don't depend on this coupon data, but it is using the atmospheric test data which people have developed and humidity data available. When I show that app in the last day, I think you will understand what it means. So this is not coming from our study, but this is coming from another study, which what they did in this one is that that's the reason that I put that table, although it's probably difficult for you to read. But what they did is they took these materials like the steel materials and aluminum material, which is used in the wind turbine, and what they did is they simulated their conditions, which they see in the nacelle and other places. That condition they simulated in the lab, and then made this corrosion measurement from that, the corrosion rate measurement from that. And so that they can get an idea about this could be the, if they use this material inside the nacelle, if you gearbox, and gearbox is having lubricant, and the lubricant, so gearbox, there are some material that is corroding. That corroding environment will be lubricant mixed with water, and in that condition, what could be the corrosion rate they can expect? And similarly, in some other places, when they have some other environment, what corrosion rate they can expect? Like that, they made this table. I felt that it's quite a nice simulation, things what they did, and exactly simulating that environment in the lab. And it can be used, kind of, they can make a model out of that, and it can be used again to predict something. That means that all these places, you need a very, very high protection level. So you can see that, like, so this is just showing that an onshore wind turbine where you have C3 conditions and the kind of thickness loss. If you expect, like if you take the tower part, kind of thickness loss you expect is around 50 micrometer per year. That's the kind of corrosion level you expect. And if it is offshore, which is C5 condition, you get into that around 4 times of that, around 200 micrometer. That's the kind of corrosion level what you are expecting, which also means that you also need to have this level. Remember that 200 micrometer itself is not a big thing. Think about you have a very thick steel tube for the tower. So 200 micrometer itself is not a big thing, but the problem is that think that this 200 micrometer is an average corrosion level. Think that in one place it is 2 millimeter, another place it is only few micrometer, like a pitting sort of thing. And then you have the fatigue issue. So most of the time the corrosion is not causing the problem, but at the end it is a fatigue. Corrosion fatigue is the one causing the problem there. If you have a pit and it is going deeper and that is acting as a crack. So that's the issue. And that means that this is just to show that it is it's quite severe in that sense. And then also you need to protect that. So that shows this protection strategy. You can just to give you a glimpse of like what level of painting they do. So that's a C5 marine condition. So this is a different standards. There is a German standard and ISO standard and this North South standard. There are different standards in relation to the painting. And but people follow one of them. It's not all of them. One of them people follow that. But it's just to show you a comparison. So whenever you see EP, it means that epoxy, resin covered, polyurethane, that is PUR, and PUR zinc rich means the PUR also contains zinc plates, so that it will act as a galvanic, like a zinc coating, and that's why it is zinc rich. And you can see that they put many layers and almost like a thickness of around 320 micrometer level. This is atmospheric exposure part. This atmospheric exposure part they put around 320 micrometer thickness, and actually the North Soak is actually much higher than that. It's go up to around 1000 microns. So it's quite a big thickness of paint which they put all together to protect it from corrosion. This is underwater and splash zone area. You can see this. So this is the atmospheric part which is coming above the tower. You don't have to worry that much about the corrosion problem. And so then they have a slightly lower thickness. And then you have the splash zone area. You can see that it goes up to 800 microns and like that. So it's go to the much higher thickness in average. So even the painting, they do it at different levels. Because you can also see that it's such a big structure. Every rupee or whatever they can save is an important thing. So they want to save a lot. At the same time, the system has to work perfectly for the period. So that's the thing. So there is a lot of things involved in that. Electronics part, I told you that I will come in the next lecture. So that's part a little bit on the wind turbine part. Then I'll get into another area. Is there any questions related to this part? Yes. Let me see what you mean. It's protected. It's this part. This part is cathodically protected. The bottom part is cathodically protected. Whatever is in the seawater, and that part is cathodically protected. Splash zone, you cannot protect it like that, right? Splash zone is dependent upon how the water is splashing and where it is wetting. So the cathodic protection may work there, may not work there. Like that. Any other things? Yeah. Yes. Yes, you are right, because maybe you remember the first table which I showed. There I was telling that acidification also can be hydrogen embrittlement, because hydrogen is produced and that hydrogen is reduced right on the surface, and that way entering it, it's possible. It's also causing the hydrogen embrittlement. I don't know about the corrosion fatigue is an issue. I don't know about the corrosion fatigue issues of how much corrosion fatigue issue is there in the failure, or I don't think that, put it this way, none of the wind turbine has failed because the tower is failed until now. Only thing is that they knows that the tower is going to fail or tower will have the problem to take care. So that's the only thing. So none of them has failed because it is that safely they made, and none of them. All the wind turbine failure until now is due to electronics, not due to the tower or other material. Electronics, which has a corrosion problem, and that resulted in fire, and so inside the nacelle it's caught fire, and then of course everything is destroyed. So that's what happened, not due to the tower failure. Tower failure, I haven't heard any wind turbine failure due to tower, but they analyze for the corrosion fatigue and all those things that they do non-destructive testing and all. I'm sure that they must have identified whether there's a hydrogen embrittlement issue, stress corrosion cracking, and all those things. So all these issues can be there. Yes, there is. This is in our department, not me, but there is another group. They are working on related to the this bearing failures inside the this gearbox because of the because of this fatigue. And there they say that yes, there is a hydrogen embrittlement is an issue there as well. Yes, it's true. Yeah. Yeah, maybe yes. Yeah. Yes.
Then how did you correct those?
I think this, those. If I'm correct, what you're talking about is like in those pictures, you see that rust coloring here, right? But that's a repainting. Yes, they did the repainting, and the corrosion may not be that much. And the question is like this: the wind turbine may work for 25 to 30 years. So whether you can extend the life until 30 years, this is a question, right? So no problem to have the like the aircraft. Aircraft wing can have a crack. As long as the crack is not critical, still the aircraft can fly. So it's exactly the same way. If they measure the corrosion level here and they know from the fatigue and different models whether that's critical or not, if it's not critical, still the system can be stable, right? So that only thing is that they need to take by the time they start seeing the corrosion, they need to take the remedial action, immediately strip the paint and paint it again, and things like that. They need to protect it, that's all. So extending the lifetime to 25 to 30 years is the thing, and not that completely stop the corrosion. Corrosion can be allowed as long as the structure is still stable for 30 years. That's all. Sorry, coupons, yeah. The steel what we are talking about, the carbon steel. So that way it's an alloy. Aluminium is an alloy. Is a 6000 series, right? That's aluminium is an alloy. But other things are comparatively pure metal, because copper is used as pure metal. Silver is used as a part of electronics as a pure metal. So those ones are pure metal, and zinc is also more or less pure like that. So those ones are the pure metals, but other ones are aluminium is an alloy and other one is carbon steel. So that's because it's imitating what is there inside the turbine. Yeah. Yeah. Tell me again. Yes. Yeah. Yes, corrosion rate data is. Are you from SICRI? No, you're not. That's what I was talking about. SICRI. SICRI is having that atmospheric corrosion test site, right? That's an example. So there they exposed many materials, and they come up with the corrosion rate data for over the many years. Similarly, there is an atmospheric test site, probably so many test sites over the world, and this corrosion data is available. So anywhere in the globe, if you take, at least there are So you will be able to find atmospheric corrosion test site at some places, and that corrosion data is available actually. Not only corrosion data, there is corrosion data for steel and other materials. There is chloride deposition data, humidity data. So there is so much information there. That information we overlapped with our climate app. So that's what we did. That I'll show you later. So that's the answer for it. Every point you don't have, but you have at many places, and you will be. And then now what we are trying is that when you have the corrosion data at some, you have these 2 points, you have the corrosion data, but you have the humidity and temperature data for in between. And using that humidity and temperature data and using the humidity and temperature data here, whether we can interpolate this corrosion data to other places, that's what we are trying actually. So there is corrosion data, there is a lot of corrosion data available from the atmospheric corrosion test site all over the world. It's a coupon method. Yes. It's a coupon method, actually exposing at different places. Yeah. 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 I don't know. You say real-time monitoring method. Sensor, right? Only thing is we are taking more time now. Is that okay? Because I haven't even finished this. We thought that we'll finish by this time. Okay? You know, like there is a paint company in Denmark called Hempel. They are the one actually making the paints for all these heavy duty paint. There's also a part in India, I think it's Pune. Like, so they make a lot of paint. And this company now working towards making an impedance sensor, and which can be below the paint. So not for normal paint, but you know, when they have the big painted buildings or painted wind turbine, it's a lot of paint, right? So there it is very important to monitor how the paint is degrading. So they are having a impedance sensor which is put below, and then they are trying to get the online transfer of data and analyze. Actually, it has happened from our lab because we use these impedance sensors so much in our electronics, because electronic structures are like that. You will see that when we go to tomorrow, that our test systems. And seeing this, we are using in the electronics these kind of comp structures, interdigitated structures. And this paint company asked me, oh, why can't we use this as a sensor for the paint? And so what happened was, one of my PhD students joined there as postdoc, and then they started working on it, and he developed it so much. So what they do is that they take the metal surface before painting, and even they can do on-site by using the robot. They make a metallic structure by printing process, and then they paint it, and this printed metallic structure is connected electrically to the system, and then they can do the online monitoring. If you do that similar thing inside your this one, and you have the paint and then the metal surface, here you have the paint and your cement and the rebar, then you may be able to monitor this one. Of course, the only thing is that what is available is that I can give you is that this comp structure and the general information on that, but all other things are like how it is electrically connected and how it is data is, it's confidential because it's company property now. But that's an example, like to see. Yeah. Electric? Yes. Humidity, yes. Yes. The good thing. Not only for that. So the nacelle, I told that most of the corrosion problem inside the nacelle is when the wind turbine is off during the repair time, because then it is cold. So one way of avoiding that is during that time you use any dehumidifier inside, and that way you remove the humidity. That's a solution for that. But the only thing is that nobody wants to do that because yeah. So many of the customers, Vestas will tell them that when they supply that whenever you are shutting down, you need to use a dehumidifier inside. But no, people will not do that. That's the issue. Go a little bit into the carbon capture and storage part now. So now the thing is that, okay, the other one is wind turbine is a low carbon technology in the way that it's not emitting the carbon dioxide, right? Because we are not using the fuel to burn and make something. So that's the way. The other way is that now to make it clean energy or clean atmosphere is that what is happening is you collect the CO2, still you have the power plants and things like that, but you collect the CO2 and then push the CO2 down into the earth, and that way you can store it, and that way it's not emitting the atmosphere. So we can say that from the power plants, factory and things like that, so there is a lot of CO2 emitted, and collect those CO2 and collect that CO2 and liquefy it, and after liquefaction, and you just push into the storage systems, and that way store it and close it. So that way you can reduce the carbon dioxide emission. So this is the kind of things what people are trying to do, and the many different technologies that are coming up. And the problem is that when you inject like that, so think about, like here it is shown this oil well, it is shown like this. So there is already existing oil well. So this is a reservoir where they had the oil. This is a well, so the oil has taken out through this well, and all the oil is taken out. So that means that this oil well is empty now. So there are many wells like that all over the world. Now the question is that this reservoir has a lot of empty space, so they can inject the CO2 down and store it in that CO2 instead of oil. And then once it is filled, and you close it, and then it has to survive like that for 1,000 years or 500 years safely without any problem. That's the condition. And so this is inside this oil well, if you take this part of the structure, it's made of metallic material. So they have this metallic tubing. Until you reach the reservoir, you have the metallic tubing, and then you have the reservoir. So this metallic tubing, if it corrodes, and then the carbon dioxide can come up. This is the thing, even after blocking it. And this is also the problem that those tubing will get corroded. That's also the problem with the corrosion in the oil and gas as well. So there is a lot of similarity with the corrosion in the oil and gas. Only thing is how it occurs is slightly different. And this material what is used here is a plain carbon steel. Why they use plain carbon steel? Also, although there is a lot of corrosion problem, it's cheap. So in order to be profitable, they use the carbon steel there. So that's the problem, that there's a lot of corrosion problem. Now when you look at the carbon dioxide is how the carbon dioxide ingestion is taking place. So they collect the carbon dioxide and they make the carbon dioxide into, say, a supercritical state. The supercritical state of the carbon dioxide occurs. So if you like this conical shape here, you can see that certain pressure level and temperature level. So you can have 50 degrees centigrade. You need up to 10 bar pressure in order for the carbon dioxide to be in the supercritical state. I'll tell you what is supercritical state. And if you have a lower temperature like that, this window, or if you have higher temperature, you need a higher pressure like that. This window, the supercritical state exists. Supercritical state is nothing but, you can take it as liquid state. Why is this called supercritical? There is a state between liquid and gas. It looks like liquid, but it is not liquid, not totally gas. So that's what is called supercritical state. Why they are interested in supercritical state? Because supercritical state CO2 is very easy to transport. So that's the reason that they want the CO2 to be in the supercritical state. So that's the case. That's the way they do. They collect the CO2, pressurize into supercritical state, pour it into the well. Even the amount of CO2 collected can be so much that it can be continuous injection. So there can be like this, a place is collected and it is CO2 will be pumped through the tubes, and it can be continuous injection as well. Now coming to the corrosion problem. What is the corrosion problem? The CO2 Supercritical CO2 itself is benign. It will not do anything. Liquid CO2 is not corrosive. The problem comes because any of the CO2 which is collected from the different sources can have some contamination. It can have a little bit of moisture content, and it can have oxygen content, it can have other type of things as a part of that. This is what is causing the problem. This water content, moisture content, and other gaseous content of tiny levels, that is what is causing the problem. That is what is causing the corrosive environment. Now, if you look at it, with all those things, what kind of corrosion problem can come? Think that this supercritical CO2 is injected through this. While it is injecting here your CO2 is in supercritical condition. When it is supercritical condition, you have very little amount of water and gases. And this little amount of water and gases can condense on the outside surface here of the tube. But that condensed water has a problem, because that condensed water is very little with these gases dissolved in that. Since it is very little water and this gas is dissolved, means the pH will be dropping down to even 1 pH level, very, very low pH level, because the pH level depends upon how much gas is dissolved in the water, right? Since the amount of water is less, even with a less amount of gases, the pH will drop. Not only that, when it is pushed in the supercritical form, everything is pressurized. When you increase the pressure, you dissolve more gas into the water. So then the pH will be very low. So all the water that is dropping out here in this condition will have a very low pH. Then the CO2 will go down, 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 go to the reservoir. Once it reaches the reservoir, during the flow, it will get depressurized. Depressurized, and once it reaches the reservoir, it becomes gas. But then there is a lot of water in the reservoir. So once it reaches the reservoir, it becomes soda. Like that CO2 is dissolved in the water and it becomes like carbonic acid. Then you have another corrosion problem, carbonic acid, because now it is aqueous phase CO2. Aqueous phase which is saturated with the CO2. Here it is CO2 phase which is saturated with a little bit of amount of water, like that. So this is a corrosion issue, and this is also the complexity of the corrosion. It is not the same, and that's what we are trying to find out. Try to find out means what they want to do at the end is that they want everybody, this is of course while we study the mechanism of corrosion, things like that, end product what these companies also want is that to make a model. That model should tell that depending on the purity of the CO2, what will be the kind of corrosion rate. That's what they want. They want to make a model to say that what will be the corrosion rate depending on the purity of the CO2. We can also look at it another way. They call it a sensitivity analysis. Sensitivity analysis means today you think that they collected CO2 from this place. Tomorrow they collected the CO2 from a cement factory. When they collect the CO2 from the cement factory, they found that then the SO2 level is 100 ppm. If they have a model, they can put this contamination into the model and say that, okay, even if it's 100 ppm, the corrosion rate will increase only 10%. It doesn't matter. You can also inject that like that. So that's called sensitivity analysis. So you can also use a model for the sensitivity analysis. This is what the kind of rough idea to come up with. Good question. You can remove everything, but then the CO2 injection costs become very high. So this is another thing. All these process of collecting the CO2 and injecting the CO2, who will do it? Some company has to do it, right? Companies will not do it unless it is profitable. So where the money come from? Where they get the money? Money is coming from, at the end, what, for example, Danish government will do is, Danish government will say that all the power plants has to pay a tax. Depending on the amount of emission, they need to pay a tax. A cement company has to pay a tax. This tax money is the one which goes to the company who is doing the injection. If they have to purify the CO2, then it becomes a non-profitable business. So that is not viable. Unless until if the CO2 is extremely bad. So that way you cannot remove the water. That's you need to inject with water or other impurities. So this is just showing that this one CO2 source, CO2 capture plant, compressed that into the supercritical form, transported through the pipeline, down into the well. So that's the way it goes. So the continuous injection from a collection to the injection into the well. So this shows that, like, different possibilities. Like, people are also using earlier CO2 to push the oil. So earlier what they do is that in order to get more oil, they are putting the CO2 down. That will push the oil, and that way they can produce more oil. And that's also a good thing, because that CO2 then is blocked there, like that. So that way also people are trying, but now it is much more focus is on just put the CO2 down into the well. So here you can see that, like, for the first case which I mentioned, that is, you have this CO2 conditions which is contaminated with very little amount of moisture. Like, you can see that this is 1000 ppm to 5000 ppm moisture content in the CO2. And I mentioned that this is what happens. So this is just schematically showing CO2 is injected in the supercritical form. As it comes down, there will be a pressure drop. There may be a special pressure fluctuations. That pressure fluctuations will make this water to drop out like a condensation. And this water will have a very, very low pH, because the small amount of water, all these things are dissolved. So that will have a very low pH condition. You get a lot of corrosion problem here. Then the CO2 is coming down into the reservoir. CO2 is dissolved in the water like carbonic acid. Then you have a pH 4 or higher than that. So this is like normal oil and gas corrosion or carbonic acid corrosion. This is what happens. Only thing is that there is, even in this case, you also have H2S, SO2 and things like that, because that's the part coming from the this carbon dioxide. So here we can see the importance of this. That is, people have done. So we collected this data from the literature and we are trying to plot it. And you can see that this is the different people have done this work, looking into, with the increase in the amount of water in the CO2, how the corrosion rate will change. You can see that with it goes up with increasing the moisture content in this one. Understandable, right? Because that moisture content makes these gases to dissolve, and that way you can have the corrosion problem. So that's what we are trying to look at it. So what we try to do is that, since we have a lot of impurities, we do this design of experiment to see that, like, really what range of composition which we need to take like that. So we study like oxygen 1 to 10 ppm and all other things starting from 10 to 1000 ppm like that, and in the lab scale. And why we do that, this 1000 ppm, because you can see that here SO2 H2S is only 20 ppm or SO2 is only 50 ppm, but in the lab scale experiment we study with 1000 ppm, because in the lab scale we are doing the experiment with not with the supercritical CO2. We are doing the 3.5% sodium chloride saturated with the CO2. At the same time, when we do that, we want to simulate this condition here. So although there is 50 ppm SO2, that 50 ppm SO2, when it is dissolved in this, it's a very high concentration you will have. So that high concentration we are simulating, and that's the reason that we go up to 1000 ppm in the testing. So then we do these different contaminations and we mix up and all those things, and then we do the DC polarization, AC impedance, and subsequent analysis with SCM and things like that to understand how the corrosion is occurring. So that's to learn the mechanisms. And why we also do this design of experiment way the experiment is, because once we do this design of experiment way, we can use this data for using our machine learning algorithm to build the model. So this is just showing a little bit of how the gas will dissolve into the water and create a different type of acid, create the carbonic acid with the CO2. You get again acid species when the SO2 is dissolved, and if you have ammonia and things like that, again you get the acid species, like the gases which is dissolving into the water phase, and its species. So at the end it will not exist as gas, but it has some of the species. That's what happens by dissolving into the into this water film. I just show you just some experiment, just some results like so we are looking at, so this is the LPR we do, linear polarization experiments. So since the linear polarization experiments, we can study the corrosion rate versus time by doing that, and we are try to study the temperature effect. So you can see that this is the 5 degrees the kind of temperature we expect when the CO2 is injected in the top of the well, and the CO2 is going down. The temperature will come to 30 to 60 degrees centigrade, because now the bottom part of the well will be much more hot, 60 degrees centigrade, and we are trying to see that how the corrosion rate is changing with the temperature. So you can see that there is a huge change in the RP value starting from 5 to 30 degrees centigrade, but above that temperature the effect is less. So there is a increase in the corrosion rate within the 5 to 30. This one we try to study the ocean concentration effects. So you can see that again, like starting from so that is 30. 2 ppm ocean when you add, there is an increase in the corrosion rate, but even if you add more oxygen concentration, it is not changing that much, because there's also a saturation value, right? For the ocean, the amount of oxygen that we can have in the water. We try to study this monoethylene amine, because amine is used to capture the CO2. So amine will bind with the CO2 and capture the CO2. That's the way the CO2 is collected. So there will be contamination of amine. And that's the reason that we tried also to study the amine. But we are doing many experiments like this, and then we do the scale analysis to see that what is forming and all those things. And so just to show a glimpse of this, like this ocean content as an example, but you can see the temperature has a very, very clear effect. So we should expect that from the top of the well to the bottom of the well, there is a very high difference in the corrosion rate because of this when they inject. We do experiments, as I mentioned that in 3. So this is another important thing. We do the normal electrochemical experiments. You are familiar with these kind of things, right? Like electrochemical cell, 3 electrode electrochemical experiment. We do in 3.5% sodium chloride. We add whatever contamination we want, gaseous state or ionic state. So we have inside this, we have the capability to get oxygen into the water. We have the capability to get H2S. You can put SO2 and all those things we can put into and CO2. We can put all those into water, that we can do the experiment like that. But this experiment will not give us a total idea, right? Because this is at atmospheric pressure. But when the supercritical CO2 is injected, it is the pressure is probably 300 bar, and it is a supercritical form. So we use the flow loop experiment, and in the flow loop experiment, we have a company which we collaborate, and the company has a flow loop, and there we can get actual 300 bar pressure, and you can get actually inside these chambers and things like that, you can get supercritical CO2. Supercritical CO2, and we can contaminate that with whatever amount of water we want, whatever amount of gas we want. So exactly like what CO2 is injected, that's what we test here. The problem with the flow loop is that this testing is time consuming and it requires a lot of things. So that's the reason that we do the lab experiment, so that we can screen the parameters here, and then we know that what are the critical parameters, and that we do it in the flow loop. Then another thing is that you are vapor phase, right? I mentioned that like you get this condensation corrosion, right? Here. And to study that mechanisms, we also build a cell like this. And in this cell, we can actually put the sample on the top of this in a specific way we make. And then we can cool down this so that we create the condensed water layer on the top by cooling down. And to this chamber, then we can pass H2S, CO2 and all those things. So this thin layer of water will be saturated with all these gases, and then we can do the electrochemistry like that, so that we can do the vapor phase corrosion studies here. We are so much familiar with this. This is now we are using it for this application, but all our electronic things that's the way it corrode. So we are familiar with this condensation setup and things like that. We also have equipment to measure how much water film is forming and all those things that you will see tomorrow. So that's a three ways we do the experiment. Sorry? No. All these are ambient conditions. Only we can do. But so we can simulate in a way we can simulate the condition and get an idea. But at the end, we need to do the flow loop. At the end. Yes, you can control the water layer thickness by adjusting the temperature. So we pass a coolant through this. Depending on the coolant temperature, we can control the water film thickness. We can go down even to 1 micrometer or lower. We can go really lower. The question is that what thickness level we can measure it. That's the question. So probably 100 nanometer to 200 nanometer is the level at which you start seeing the electrochemical current can pass easily, and that way you start getting the problem. Let us discuss that tomorrow, because tomorrow I'm going to show more things related to that. We also use, in this work, we also use a lot of X-ray tomography and synchrotron, because we also want to understand what is the scale that is forming here and how the scale is building up with time. So what we do is that we use the tomography so that we can do this 3D image. So here you can see the difference between 0 chromium, 1 chromium, 3 chromium. Clearly you can see that why they add chromium into the material. You can see that in this particular case, there was this scale, right? Corrosion product. So this is an X-ray image, 3D X-ray image. There was corrosion product scale, but in this image, by image analysis, we can remove that corrosion product by image analysis. So this is after removing the corrosion product of this one. So when you remove this corrosion product, that's what you see. This is the metal underneath, the way it is corroded. 0 chromium, you see there is a lot of corrosion, and with this one, it becomes much more smooth when 1 chromium, because chromium is protecting, become very smooth with the 3 chromium. So you can, just by looking at it, you can understand what is the advantage of adding chromium into even 1 chromium into the alloy. So then we want to understand how this layer is building up, because when you analyze this layer, you will see iron oxide, iron carbonate, and different things. So we want to analyze that. So that's the reason that we use the in situ synchrotron, where we can have this kind of cell with the specimen, and we can put this one into the synchrotron, inside synchrotron, and then we can do the X-ray diffraction in situ. You have high energy X-rays in the synchrotron, so you can do the X-ray diffraction in situ and understand what kind of corrosion product is forming on the surface. So one side we do a lot of mechanistics type of understanding, other side then we do this corrosion data build up so that we can build the model. So we have many projects in that, looking into different things, but idea is at the end, if you get the corrosion data, then we can develop a machine learning model, which then people can use for sensitivity analysis. Okay. Fuel cells and electrolyzers, I don't have so much to tell. Probably the group here is maybe better to tell more on that, because Lakshman's group is working on that area more. But the thing is that all these, I just put this one to say that it is like this is the fuel cell or electrolyzers area also has a corrosion problem. There is a lot of corrosion problem to solve. There is a lot of things that which the corrosion people can involve. One of the main thing is that in this case is that it is the bipolar plates, because these bipolar plates are made of usually metallic one, especially because you don't have to use a metallic material, but you can also use other material. But the thing is that the bipolar plates has to be channeled like this with this shape in order for the fuel to go through. Like you can see that you have this hydrogen is passed. So if you look at in the fuel cell, you put hydrogen and oxygen on one side, and that way you produce the water, and that way the energy is produced. So the hydrogen and oxygen combine together produce water, and during that period, during that process, you get the electron flow, and that's what you are getting it as energy. So there is this bipolar plates, which is where this fuel is going through with this kind of shape. And so in order to make it like that shape, the metallic material is the best thing to do that, to make that, by machining and things like that. So there is a lot of material, metallic material used here. You can see the environment here is not that nice. because you have acidic condition and things like that. So the environment is not very good. And that way there is a lot of corrosion problems related to these bipolar plates. And so that is something which many corrosion people are looking into because of this environment in the bipolar plates. Not only that, if the bipolar plates corrode, there is another issue. It's also contaminated other areas in this membrane and things like that. Other area also get contaminated because of this corrosion problem. So that's one of the serious things which in the fuel cells. So especially this kind of design is also a thing, because this design also can increase the corrosion problem, right? Because this is much more rough type of surface, that also can increase the corrosion problem in this case. A similar way, you also have the problem in the alkaline electrolysis. And alkaline electrolysis also, the problem is that they use the nickel electrodes for the alkaline electrolysis. And but when the alkaline electrolysis stacked together, there is many other materials coming as a part of this, as a pumping system and things like that. There are many other materials. So there is stainless steel at many places. The stainless steel is dissolving. Alkaline electrolysis is done at a 30% KOH. 30% KOH, you can imagine the alkaline condition that makes some of the steel material to dissolve. And this steel material is dissolving into the electrolyte, means in the electrolysis process, that will come and deposit on the cathode. Because it's a cathodic process, right? In the cathode, you have a reduction process. So whatever metal ion is getting into the solution, and that will come and deposit. So if the chromium is dissolving from the accessory materials, chromium will come and deposit and change the efficiency of the electrode. So this is the issue with the electrolysis process. So that's why you can see here, that is, this I took from the literature. They studied the corrosion of many different alloys. All these corrosion is in the alkaline 30% KOH conditions. And why they do that? Because they want to understand that when they use as an accessory material in the electrolysis, what is happening. And we don't work in that area that much, but we are going to get the first project in this area from June. And in the alkaline electrolysis part, looking into the accessory material corrosion and how that is going to degrade the cathode efficiency and things like that. Actually, there are more problems than this just corrosion and deposition, because this material also can have a stress corrosion cracking problem in some cases, because the stresses involved and things like that. So there is a lot of things also to do in these things for the corrosion people. There are many other energy sources which we don't discuss today, but there is energy systems corrosion issues there. Geothermal energy is a big thing in Iceland. And there is a lot of materials used there in like oil wells. There's a lot of corrosion problem. Solar energy, I didn't take that into consideration. Solar energy, there is a lot of corrosion problem. These days also people are talking about hydro energy storage. I'm just submitted a proposal together with other people. I just involved in that. Somebody else submitted from Norway, where the hydro storage means it is like our dam here. Basically, pump the water when there is excess energy, and then use that for doing the turbine, and then this pump back that water again when there is excess energy. That's the idea for hydro storage. And there is a lot of pump systems and things like that is involved here. Again, there is a lot of corrosion issues. Another thing is that when you have these water sources here, probably sometimes they are using the seawater, and seawater is very corrosive in this case. So another energy storage system is coming is molten salt. So that means that whenever there is excess energy, you take a salt, like think about sodium nitrate or sodium chloride. At high temperature, it will melt. So whatever energy is there, excess energy is there, use it to melt this one and store it as a molten salt, and then use that molten salt to create the steam, and that way to make that run the turbine when you need the energy. So there are many ways people are trying to store energy. Melting the salt. There is another one in which some of the Danish companies are involved, is rock storage. Rock storage means just take a big rock and heat it, and then when they want the energy, just put more like putting a fan. blow out the heat energy, which then they use it for boiling the water to create the steam and rotate the turbine. It's just a big piece of rock is used for storing the energy. So there are many storage systems are coming up, and I think everything will have a lot of corrosion problem as well. There is electronics, which we'll look tomorrow. Okay, so I think that is what I have here. Is it become too late now? So I think what we can do is that Kahoot we don't need to do now, and what we can do is when we have practical session, I can do the Kahoot with one group, and then the next group comes, they can also have the Kahoot like that. Shall we do like that? But all of you need Kahoot in your mobile. Yeah, any questions you have? Any additional? I think this is this one, glass epoxy. Glass epoxy. I think it is that one. I don't think it's carbon fiber. I think it's glass epoxy composite. You understood when I say glass epoxy, right? I think it is that one. I'm not totally sure, but I think it is glass epoxy. Carbon fiber will be too costly for that. I think so. Yeah. Life will be increased, but if you can get, it goes like this, right? If you can get a 2 centimeter thick steel plate, steel tubing, if you can work that can work for 30 years. And although probably half of it will be corroded by the time of the end of the life, that is still cheaper than putting the spray, right? So that's, you understand my point. That is, corrosion is allowed. Only thing is that it has to survive for 30 years. So that's the way the life cycle analysis comes. In oil and gas is also like that. Like they put a 9 millimeter tube thickness, and they know that probably by within 10 years, probably 1/3 of the thickness is gone, but still the well will survive. That's fine. Still, it will have sometimes accidents, yes, because in one case they expected that the 3 millimeter is going in uniform condition, more or less uniform condition. In one case, because of some reason, it had a very huge localized corrosion, made a hole, oil started coming up. So that's one accident sometimes happens. So most of the cases it is safe to use like that. That's all.